All right, guys, let's get started. I just had a couple questions about this Pearson homework, and it kind of seems like maybe it's just like a poorly structured question, because this is the right answer, and I just saw somebody that didn't have this labeled, and it didn't register, so that's frustrating. So I'm just going to grant everyone full credit for that right now. But you should know how to, those other things, I do want you to know how to label those. It's just that those other blank boxes don't mean anything to us because the baseline is an arbitrary value, so that it doesn't make any sense. So that's granted, but you should be able to label reactants, activation energies, transition states, and intermediates, and then the products. All right, so if that was haunting you, now you can banish it. All right, a couple other announcements. So tomorrow when you go to recitation, you will be taking your exam. You're gonna bring a photo ID, all right? You have to have that. You have to give it to your TA, and then they'll give you your scratch paper. That scratch paper has a periodic table and the equation sheet that you guys have, that I've posted on Carmen, so those will be there for you. You'll have some writing utensil, one of your approved calculators, which is 4 TI levels. You need your phones or whatever you use to do your Duo login. First, then you'll put that away, and you'll have a charge device that can hold charge for an hour, and then it has updated lockdown browser. Okay, so I just checked, and then the last piece here is that it covers chapters 13 and 14. Reminder, we have office hours right after class today. Instead of being in my office, they're in a classroom, Evans 2004, and that'll be for an hour. If you have never done lockdown browser before, I really recommend going through the process, and we have a practice lockdown browser test. So if you've never done it before, please make sure you know how to do that. Right now, 65 of you have done it. There's obviously more than 65 of us. So if that's you and you have never used lockdown and you haven't tried this, please make sure that you can do it, because I don't want you to come in and then waste the first 10 minutes of the exam struggling with lockdown, because you won't get those 10 minutes back at the back end. Your exam will close after 50 minutes. Questions on logistics, what's going to happen tomorrow when you go to recitation? There are 20 questions, just like the practice exams. Okay, one other thing I want to point out. So if you have numerical questions, which you will, look at this in bold statement here. We don't ask you about significant figures because Carmen can't handle that. We say answer to 2 decimal places, okay? And don't include the units, all right? And so here you would write in 57.78. This is a bad representation because on our Carmen exams, we have margins built in. So probably on a question like this, it would be plus minus 0.05 or something like that. So there's a little window in there. So if you have a slight rounding difference, that would get caught. So I put in 57.76. That gets counted as correctly with that margin of plus minus 0.05. Okay? So just make sure you're reading those directions, because if you put in text like the units, Carmen will say that's not the right answer, and you won't get credit. All right. You're all ready to actually take the exam. All right, then we're going to begin with our first question on a multi-step mechanism. If you downloaded this early, I did change this question. I swear this is the only question I changed. I just sat down and did it this afternoon and was I don't like the way I wrote that question. This is now A, it used to be F, and now we don't have a catalyst. All right, so if you did already do this, now you get to do it again because it's slightly different. All right, so I want you to start by writing the net reaction, and then I want you to determine the rate law and identify the intermediate. Okay. Let's start off at the beginning here. What is the net reaction? For this, you take all of your steps, add up all of the reactants, add up all of the products, and then cancel anything that shows up on both sides. So here I would have F plus B plus D plus E goes to D plus A plus G, and I'd recognize that D showed up on both sides. So my net reaction is F plus E plus B goes to A plus G. All right? And you'd look at this, let's say I had oriented this in a different way, and I said, hey, here's the overall reaction. Do you think this is a single elementary step? And you'd say, no, because there are 3 reactants, and it's termolecular, and it's really unlikely that that would actually happen with any significant rate. Okay, so I'd be like, no, this reads to me definitely as a multi-step mechanism. Okay, and in this orientation of the question, we've provided you with a proposed mechanism, all right? And so we have to write the rate law off of that. You find your slow step, which is the second step in this case, and you write it based on the reactants in that slow step. So rate equals K times the concentration of D times the concentration of E. And then you'd stop yourself and be like, D was my intermediate, that thing that we made and then we consumed. I don't want to have that in a rate law. So I'm going to rewrite that using my fast step, assuming equilibrium. So using the equilibrium method, I will redefine the concentration of D in terms of my reactants. So that's assuming this fast step reaches equilibrium, which means that the forward rate equals the reverse rate. Okay, so I could write this as K F times B equals K times D. To solve out for D, I just divide both sides by that K, and I'm not even bothering to specify what the K's are. There's just going to be some K at the end of the day. So I will have the rate equals K, and you might see it written as just K or K obs. There's just some number there, and then we have E times F times B. Okay. The other way of seeing this question would be I give you this rate law. I say, hey, this is what we observed. And then I give you 5 different mechanism options. And you have to decide which mechanism would give you that rate law. That is how, on the first practice exam, the multi-step mechanism question is presented. And there's no way of getting around it. If I give you 5 mechanisms, you're going to have to go through and solve for the rate law for each one, and then be like, oh, this mechanism gave me the observed rate law. That must be the mechanism. Okay? That way we get you to do a lot of work. Okay? And then, of course, the intermediate here is D, because it was produced and then consumed. That's our definition of an intermediate. Questions on this? Yeah. The rate law. Yes. So I start by saying, write it for the slow step, which is the rate determining step, right? That's like you exiting the classroom, getting through that door. It's going to overall depend on that. All right, so that's how I got K times D plus E. These are both elementary steps. And so in this second step, I am literally waiting for D and E to hit each other. And so their rate will depend on the concentrations of both. So that's where I get this first equation. But we have a problem as chemists. We don't like defining these equations with an intermediate concentration. Okay, those are hard to track. They fluctuate. And so we're like, we want to get rid of that. Okay, they're usually very small. So we're like, okay, how can I redefine them? Well, assuming equilibrium in this first step, which I can because it's fast, okay, then I can rewrite the concentration of D using F and B by assuming that the forward rate of that first step is equal to the reverse rate. And then I say, oh, I've got a new definition of D, and I plug it back in here, and that's how I wind up with the final rate law. Does that feel good? Okay. All right. Let's talk, we're going to talk just briefly about catalysts. I just need you to know these. These are like basic things you need to know about catalysts. A catalyst will raise/lower the activation energy of a reaction. Thumbs up if it's raised, thumbs down if it's lower. Good. It lowers the activation energy. Okay? This might be uncatalyzed. It could be a totally different pathway, but this catalyzed pathway better have a smaller EA than that uncatalyzed pathway. Okay? The addition of a catalyst results in faster, slower, or the same rate of reaction. Let's go 1, 2, 3. Which one is it? Good, you all know it's 1. It goes faster. I could extend this and say a catalyst increases the magnitude of K. Right? Because K equals A times e to the negative EA over RT. And the catalyst is changing this value. It's making it smaller. When that is smaller, K gets bigger. A bigger K means a faster rate. Because remember, we just plugged this straight into our rate law. If the number is bigger, then the rate is bigger. Okay? So these are just some basic things you need to know about catalysts for tomorrow. All right. Let's do a mathy question. All right? We all ready for a mathy question? The decomposition of ethyl chloride at high temperatures is first order, and the rate constant is K equals 1.6 times 10 to the negative 6th inverse seconds. How many hours will it take for 75% of the ethyl chloride to decompose? All right, pull out, if you don't have it already somewhere on your computer, or maybe you've printed it, find your SI. Go find the equation that you need for this question. Okay, hopefully you at least had the time to pick the right equation. Okay, so I see first order, and I see that I'm asked for time. I know that the only way to get time into my equation is to use an integrated rate law. So on my SI, I pull the integrated first order rate law. That is the ln of A at time t equals negative KT plus the natural log of the initial concentration. Okay, and at this point you might be like, well, what do you mean? I don't have AT or A naught, so how could I solve for this? So if you're at that moment, I would be like, okay, well, I can get to T. Let me just like set this up for T because I know that's what I want to solve for, and then I'll deal with the lack of information later. Okay, so I'm going to subtract ln of A naught from both sides. All right, and then this is hopefully where you would catch yourself and be like, oh yeah, log rules, right? ln of A minus ln of B, that equals the natural log of A over B. So I can condense this into the natural log of AT over A naught. That fraction right there, that is the fraction of reactants left, okay? And I know that, right? I am waiting, I'm asking how much time it takes for 75% to decompose. That must mean that I have 0.25 fractionally left, or 25% left. So that's what I can plug in there. I can do these first order questions without exact amounts as long as I have a percent or fraction left over, okay? That's only true for first order. I can't do this type of question without exact number for second order, okay? So I'm gonna write ln of 0.25 equals negative kt. We've got k, we're just gonna plug that in. So I'm gonna rearrange, divide both sides by k, well negative k, and I have ln of 0.25 divided by negative 1.6 times 10 to the negative 6 inverse seconds. That's going to bring seconds back up for me. So my answer initially will be in seconds. I got 866,434 seconds. And before I put that in, I'm going to read the question again and be like, they didn't want seconds. They wanted it in hours. So I'm going to convert to hours. All right? So always reread the question and make sure you're giving us what we ask for. My final answer was 241 hours. Yeah. So remember that AT, okay, so the question is how did I know this part, right? That's like the really important part of this question is how do I know that AT over A naught is the fraction left, okay? A naught is how much I started with, right? That's the initial concentration or milligrams or moles or whatever I've been given. AT is how much I have at time t. So it's going to be a smaller number because this thing is decomposing. I'm looking at a reactant. Okay, so I could have given you exact numbers. It could have been like, oh, we had, 100 mgs to begin with, and at time t, I had 25 mgs. That would be the same as saying 75% has degraded or decomposed. Does that feel better? Mm-hmm. Yes. 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 Yeah, I just had, so this here is just me at this point saying like, here's what I had left before. I subtracted ln A naught from both sides. I had negative kt left. I'm solving out for t, so I divided both sides by negative k. Yeah. Did other people, oh yeah. Oh yeah, you could, because it's 75%. Yeah, so it'd be like after 2 half-lives. Okay, yeah. In theory, yes. I think that would be the harder approach, but yes, you could. Yeah. All right. So straight into another mathy question. All right, so the important thing here is, can you read this and see what equation from your equation sheet you need? All right, so we are told that we have a reaction with a rate constant of 0.2 inverse seconds at 25 degree seconds. You're given the activation energy, and then we want to know the rate constant at a new temperature. All right, so this should be ringing in your head. Okay, rate constant as a function of temperature. Arrhenius hopefully is coming to mind, okay, because that's how K depends on T. But then you're like, oh, I don't have an A here. There's no mention of the frequency factor. So we must be doing a math problem with that third equation in the row. the 2-point Arrhenius. So that was ln of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. And in this case, you'll be solving for K2. All right? So this question, the thrust of it is, hey, can you look at those variables? This is what you're given. You've got 4 of them. We're asking for the 5th, and then pulling the right equation. And then, of course, doing the right unit conversions and the right calculator punching. Yeah? Well, because I know that, so let me highlight what we have. We were given, here's K1, and it was at T1. And then here's our activation energy. And then we're asked, what is the rate constant? So a second rate constant at a new temperature. That would be my T2. It doesn't matter which way you define T1 and K1, or the 1s versus 2s. Is this yours? So you just need to make sure that you pair them correctly in the problem. Yeah. Okay, so try and get these numbers plugged in. This is, you have R on your sheet, but you have 2 different R's, right? So you gotta get the right one, okay? A clue here is that our EA is in kilojoules, so you want an R that is in joules, okay? Definitely not the one that's in atmosphere. So I'd look at that and be like, oh, that means I want R equals 8.314, and that's joules per mole Kelvin. Okay, and then I'd be like, okay, since I've got R underneath EA, I could either have taken this R to kilojoules, or my preference is to say that EA equals 41,900 joules. This is a really common place to make a mistake, is if you don't have those, if you divide kilojoules by joules, you're gonna get the wrong answer. You have to have those units matching. So write them out, write your units out. A kilojoule is 1,000 joules. All right? And then the other thing is, oh, you look at R and say, hey, that's in Kelvin. I better convert my Celsius to Kelvin. Another great place to make a mistake when you're moving quickly on the exam. Okay? So you'll plug in all the numbers. And you make sure to use like a lot of parentheses. All right, so I broke this down. This equals, that first term here, I had 5,039.7. That's in Kelvin, which is good because I'm going to multiply it by 1 over Kelvin, and I want this to be unitless. Okay, so that 1 over 313 minus 1 over 298, I got negative 1.608 times 10 to the negative 4th inverse Kelvin. All right, so then I take the product of those, and I wind up with ln of 0.200 over K2. This is in 1 inverse seconds, which is useful to remind myself I need K2 to be in 1 over seconds as well. So I got negative 0.810 when I multiplied these two. And I say, I want to get this out of the natural log, so I raise both sides by e, which gives me 0.200, 1 over seconds, K2 equals 0.445, which is actually quite close to our final answer. But what we need to do is rearrange this one more time, and K2 will equal 0.200, 1 over seconds divided by that 0.445. And my final answer was 0.450. And then at this point, after so much calculator pushing, I would stop and ask myself, is that a reasonable answer? Okay? So what would I be considering? All right? I had a rate constant of 0.2 at 25 degrees Celsius. I then increased the temperature to 40 degrees Celsius. I should get a rate constant that is slightly larger than my original rate constant. And I got that. Okay, so that makes me feel better about this answer. I turned up the temperature a little bit, and my K got bigger. Not by like a factor of 1,000, but almost doubled, okay? That feels right. Yeah. So you'd solve it as Kelvin and then bring it back to Celsius. No. Yes, this is a good point. So on the exam, if this question had come to you as a multiple choice, and there were answers, let's say some were negative, some were less than 0.2, some were like 1,000 times bigger, I would go through and I would eliminate those immediately. So let's say I was running out of time on the exam, I can't do this calculation, and there were 5 options. I could eliminate 3 of them and give myself a 50-50 chance to get the question right if I was just looking at what ballpark, what would I expect. I really encourage you to do that too. Okay, that's just smart test taking. On multiple choice, eliminate answers that don't make any sense. Yeah? Because I can't increase the temperature of a reaction and expect it to go slower. If it was lower, if I turned up the temperature and I got a K2 that was less than 0.2, that doesn't make any sense. It's got to speed up, which means the K needs to get bigger. Yeah? Yes. So I could expect it to be lower than 0.2 if I had taken this reaction from 25 down to 15. Then I'm looking for a smaller K value. Okay. Let's do some graph questions, all right? Take a second before you answer any of the statements. Look at the axes. What type of graph is this? Okay? We have ln of k versus 1 over t. That is the natural log transformed Arrhenius. Okay? So if I were doing this on the exam, I'd write underneath it ln of k equals ln of a minus ea over r, and I like to split the 1 over t out because that makes it really clear that my slope is negative ea over r, and that my intercept is the natural log of my frequency factor. Yes, that's on the formula sheet. Because I looked at my axes, and I know that, hey, I am changing temperature, and I'm tracking how K changes. So we're doing true or false statements. So give me a thumbs up for true or a thumbs down for false. So the first statement here, both reactions are first order. They have to be first order. Is that true or is that false? Good. This is an intentionally tricky question. I don't have enough information to tell you if this is first order or second order. Okay? I have no information about the order, right? I don't have any units for K. I don't have any graph that relates concentration to time. I only have the Arrhenius. And that Arrhenius works for first order or second order. I don't know. Okay? So that's a false statement. I don't know that these are both first order. But your knee-jerk reaction is to say, hey, I see a natural log. That reminds me of the integrated first order rate law. That's why you might associate it and say, hey, I know that's first order. You don't, unless I were to give you units for K. All right, the activation energy of reaction 2 is greater than the activation energy of reaction 1. Is that true or is that false? Give it a shot. You're on the test. You're sitting at your computer. You might as well answer this question. Okay. I would say that this is true. All right, why is this true? Well, this is a much steeper line for 2. So that would be like a negative 100 slope, okay? Maybe this reaction 1, my slope is negative 50. Remember that these slopes equal negative EA over R. So if I'm going to solve for EA, R is a constant, on reaction 2, I would have EA equals 100 times R. For second reaction, I would have EA equals 50 times R. You all know that 100 times R is a bigger number than 50 times R. My activation energy must be larger for that second reaction, okay? How about this third one? The frequency factor of reaction 2 is greater than the frequency factor of reaction 1. Is that true or is that false? Force yourself to answer. You're on the exam. There's no harm in guessing. Okay, that is also true. For this one, I'm looking at the intercept, okay? And this is going to track, even though this is the natural log of A, if this is 100, I'll use other numbers, 70, and this is 40. 70 is going to give me a bigger ln of A. Remember, because to do that, then I would have the ln of A equals 70. So take E, so A equals E to the 70th. That is bigger than E to the 40th, which is what I'd have for that first reaction, okay? All right. I just wanted to remind us real quick, maybe I should have reoriented this, but let's look at the Arrhenius equation. You all should know what factors impact K, okay? EA, we've already said this. EA goes up, K goes down, okay? They're inversely related. Temperature goes up, K goes up. A goes up, K goes up, all right? Importantly, you will not, on the exam tomorrow, say that K is impacted by concentration. The concentration of the reactant does not show up in that equation. So changing the reaction concentration, or the reactant concentration, has no bearing on K. Don't answer that. It's inversely related. So if I were to, so mathematically, if I were to say, okay, K equals E, now I'm just going to say, like, let's say this is a bigger number up here, E to the negative 100, versus now let's say it's a smaller number. So let's say I'm doing subpar math right now, but I'm just trying to prove the point that here, if I had lowered it, E to the negative 50 is a larger decimal than E to the negative 100, because it's a negative exponent. Does that? Oh, why is that true? Like physically? Yeah, because if this is a big value, okay, all of my reactants, when they collide, they need to have energy to get over that barrier, okay? And it's just like energy is a distribution, okay? So I'd look at the like kinetic energy of my particles, so the percent particles. All right, let's say I'm at some temperature and this is my distribution. If EA were here, now only this fraction can get over it. Because my particles have to have enough kinetic energy to get out over that barrier, okay? So if EA is lower, if EA is higher, then, now I'm confusing myself as I talk through this. because I'm drawing the wrong direction, like a champion. Okay, so if that were my EA, okay, now all of those particles over that, above that, those are the ones that can get over it. Does that make sense, that fraction? Okay. Now, if I increase EA, and now I have EA over here, the fraction that have greater than that is that little nub right there, the little blue spot. Now only 5% can make it over because I have such a big activation energy. When it's lower, a much larger percentage of my particles have enough energy to make it over. Does that feel comfy? Okay. All right. But no concentration. Don't get lulled into answering that. All right, let's really switch gears, because that's what's going to happen. Your questions are going to come at you out of order. So you might go from something about the Arrhenius all the way back to something about saturation. All right, so I put 50 grams of potassium nitrate into 100 grams of 20 degrees Celsius water. I want to know the molality of the solution. And I put the graph on there for a reason. Don't ignore the graph. You need the graph to solve this problem. All right. First question. Do all 50 of those grams dissolve? No. So that's the key here, is to say I went past the saturation point with that 50 grams. At 20 degrees Celsius, I can only dissolve 30 grams, okay? So when I'm looking for the concentration, I'm only going to use 30 grams to calculate my molality, because only 30 grams dissolved. There's going to be 20 grams of potassium nitrate sitting at the bottom of the vessel, okay? So there should be 20 grams sitting, and we'll say solid KNO3 sitting at the bottom. Okay, so to calculate molality, which is moles of solute divided by kilograms of solvent, I'll convert 30 grams to moles. And then divide by 0.1 kilograms, because that's my amount of water that I have. I came up with about 3.0 molality. Per the last question here, where I identify each solution as saturated, unsaturated, or supersaturated, this is a saturated solution. I can't put any more salt into solution. I could put it in there, but it's not going to dissolve. I can't dissolve anymore. Okay? Second question, I turn up the temperature. Now what happens to the concentration? Okay, and then I go to 40 degrees on this. And I'd say, well, at 40, my solubility has really skyrocketed. At 40, I could dissolve 63 grams of potassium nitrate. So all of my 50 grams should have dissolved now, okay? Because I'm underneath that line. Underneath the line means that I am unsaturated. I could still put a little bit more in. So I'd recalculate this, but now my molality will be from 50 grams of the potassium nitrate. And now, even though this is a higher concentration, this is unsaturated for this temperature. Right? Because we would be right here. So under the line is unsaturated. Okay, at the line, if you were right at the line, that would be saturated with no solid at the bottom. You're like right at the tipping point. Any more that you add in would not dissolve, or you'd reach that equilibrium where, of course, you still have some dissolving. You have stuff precipitating as well. And then, so up above the line is saturated. And then for a supersaturated, I would have to tell you something specific about how I produce this. Usually that is like, hey, I heated it up at a very high temperature, got a bunch to dissolve, and then slowly cooled it back down and like didn't disturb it at all and kept that in solution. It's called metastable, but you wouldn't get it by accident. So nothing about this here would tell you that I was trying to get that. So that comes from the beginning where I say I put 50 grams of KNO3 into my 100 grams. Initially, it didn't all dissolve because the water was too cold. I turn up the temperature, all of it dissolves now. Okay. A colligative property question, but about measured Van Hoff factors. All right, the freezing point of a 0.12 molal aqueous solution of calcium chloride was negative 0.52 degrees Celsius, okay? The KF of water is 1.86 degrees Celsius per molal. What was the measured Van Hoff factor? And then on the next slide, I'll remind you why the Van Hoff factor changes in reality from what we expect. Just, we're looking for I measured, yeah. So the math for this is not too tricky. Don't overthink it. So again, let's put yourselves into your shoes. Tomorrow you're sitting on the exam and you have your SI and you're like, okay, they're asking me about freezing point and the Van Hoff factor. I will grab the freezing point calculation, or the freezing point equation. That's delta TF equals negative I molal, and the lowercase m, KF. All right? We are given the measured, say the freezing point, and I could have strengthened this by saying the freezing point was measured to be. This is the real freezing point. Okay, I went into lab and I did this. I know that it's negative 0.52 degrees Celsius. I know that now that relates to I measured, what the real Van Hoff factor was, times molality, times KF for water. All right, so I'm just going to divide both sides by negative 0.12 times 1.86. I got an I measured of 2.33. okay? And then I'd stop myself and I'd be like, oh, does that answer make sense? What was the expected Van't Hoff factor for this salt? Show me with, thank you. Yes, good. 3, calcium chloride I would expect to split up into, if it dissolved, Ca2 plus and then 2 Cl minuses, right? So 3. But at this concentration, at this high molality, I don't have an I measured of 3. I have an I measured of 2.33. All right, the expected I, so I expected is always greater than the I measured because of. All right, so let's remind ourselves about ion pairing. Okay, so here's the table. All right, we see here, all right, we're looking at a non-electrolyte. It's always 1, that doesn't change. Then we have NaCl, which has an expected of 2. But as you see, I wish they had oriented this the other direction maybe. But here's what we expect, because that would be Na plus and Cl minus. All right? But and at this low concentration, we're pretty darn close to 1.97. Sorry, to 2, because it's 1.97. Words are hard. As we get to higher concentrations, so at a 0.1 molal, we have a measured I of 1.87. So now we're deviating fairly significantly from our expected value. So we can say the general trend is that that I measured decreases with increasing concentration. And then we could even expand on that and say because ion pairing is more prevalent. All right, why is ion pairing more prevalent? And what is an ion pair in the first place? An ion pair is when our cation and anion come back together in solution. They say, let's hang out. And now all of a sudden what was 2 particles is only 1 particle. And remember, our Van't Hoff factor measures that amount of fragmentation. And so when we ion pair, the number of fragments goes down, and so our Van't Hoff factor needs to go down too. All right, so we see the trend with concentration, and the other thing we want to point out is that when you compare 2 salts with the same expected value, the salt that has the higher charges, so magnesium 2 plus and SO4 2 minus, notice that these factors, these Van't Hoff factors, I measured decreases more for higher ion charges. Okay, it's these 2 points that are really useful to compare. Because at that 0.1 molal, NaCl has decreased, but it's still 1.87. But magnesium sulfate's all the way down to 1.21. That tells us that there's a lot of ion pairing in that magnesium sulfate solution, more than in the NaCl, because a +2 charge and a -2 charge are more strongly attracted to each other per the Coulomb force or electrostatic force, okay? So they're going to draw together more regularly in solution. All right, that was our crash course on the Van't Hoff factor. Now let's talk about Raoult's law. All right, the pure vapor pressure of benzene at 25 degrees Celsius is 0.841 atmosphere. Okay, you'd start just reading that question, you'd be like, I bet this is a Raoult's law question because I was just given vapor pressure. Because you have a vapor pressure, you know that we are going to consider benzene as a volatile solvent. Remember that volatile means that you have a measurable vapor pressure. Well, we gave you a vapor pressure. We measured it. It's non-zero. Okay? So we have a volatile solvent. That's benzene. And I want to know how many moles of non-volatile solute, I don't even name it because it doesn't matter what it is, as long as it dissolved and went into solution. I don't care what it is. I just need to know how much because it's a colligative property. Okay, so how many moles of that solute did we add to 100 grams of benzene if my vapor pressure dropped to 0.72 atmosphere as a result of that addition. Okay. Your mind chew on that for a second. Again, if you were like, I have no idea where to start, go to your equation sheet. There's always an equation. Okay? The only equation we have that has pressure in there explicitly right now, I think that's true, is Raoult's law. So the vapor pressure of our solution is equal to the mole fraction of our solvent, and I'll be more specific, we'll just call it benzene in this case, times the vapor pressure of the pure solvent. All right? We are given two of those numbers right off the bat. We have the vapor pressure of pure benzene. That's 0.841 atmosphere. And then I tell you, hey, I added some stuff in there. I made a solution, and now my vapor pressure is lower. That's my P of solution. Okay? So this is my 0.841. This is my 0.72 atmosphere. All right, so even if you were like, I don't know where I'm going with this, at the very least you could start by saying, hey, I can solve for the mole fraction of benzene, and then I'll deal with the next step after that. All right, so the mole fraction of benzene equals the pressure of the solution divided by the pressure of pure benzene. That's 0.720 divided by 0.841. And now I know that 0.856 is my mole fraction of benzene. In other words, 85.6% of the particles in that solution are benzene. Or I could say like 15% are the solute that I just added. All right, so now I know the percentage that's this non-volatile solute, but I'm asked for the moles. Okay, so you could rewrite this and say, what's the definition of mole fraction? Okay, you'd pull that out because I told you to memorize these things. You'd say the mole fraction of benzene equals the moles of benzene divided by the total moles, which I could write out, but I'd rather at this point say I know that that's equal to the moles of benzene plus the moles of solute. And there's the variable we're trying to solve for. Okay, we know this fraction. It equals 0.856. Do we know the moles of benzene? We sure do, because I told you that it was 100 grams of benzene, and I've kindly provided you with the molar mass. So now we can solve for moles, and now we have one variable left, and it's our moles of solute. So I'm going to find moles of benzene. All right, so now I'm going to plug that in to these two positions, okay? So I've got 0.856 equals 1.28 divided by 1.28 plus x, the moles of the solute. All right, so you got to do a little bit of algebra here. So I have 1.28 plus x equals 1.28 divided by 0.856. That equals, oh, I didn't calculate that. I'll write it out for you. 1.28 divided by 0.856. Okay, so that's 1.49. And so x is equal to 1.49 minus 1.28. I must have added 0.22 moles of solute. So if you're wondering how could we make a standard Raoult's law question a little bit harder, a little bit more involved, this is a good example. Yeah, no? Yeah. Henry's law? Because Henry's law is for a, when? When would you use, when I am explicitly asking you about the solubility of a gas in a liquid. So I gotta tell you that the solute I'm looking at is a gas. That's when I would consider Henry's law. Okay. And notice here that we were able to predict this change without any knowledge of IMFs, right? Because we assume, this is the assumption, assume an ideal solution. Raoult's law defines an ideal solution. Okay, where IMFs don't matter, another way of writing that is saying delta H of the solution is about 0. It's not exothermic, it's not endothermic, because my solute and solvent particles like to interact with each other exactly the same as they interact with themselves. Okay, so stepping out and putting a little bit more like the conceptual, qualitative info into this question. Okay. I'm going to skip this question. You guys want to skip it? Oh. Let's do it. Never mind. Go ahead. I just feel like I'm very calculation heavy right now, but tomorrow's going to be a calculation heavy test, so you might as well accept it. What is the osmotic pressure of a sucrose solution? Okay, so again, you'd be sitting there and you'd have your exam sheet and you'd say, okay, I need osmotic pressure. That's pi, the big capital pi. And you'd write down that pi equals I, big M for molarity, RT. What is I for sucrose? 1. It's a non-electrolyte. Okay, you look at that formula if you didn't know that and you'd say, hey, I don't see any metals. I don't see any ionic compounds. Molecules dissolve in units, in their molecular unit. They don't split up, okay? So I can look at this and say that should be 1. Right, and then for molarity, you bring that definition. You say, I know that molarity is moles of solute divided by liters of solution. All right, so I need moles of sucrose. You have the molar mass right there. This is in 1 liter. This should be a fairly straightforward calculation. So 85.5 grams divided by 342 grams per mole over that 1 liter. I got 0.25 molarity. Okay. And then R. And now you're going to remember this is an osmotic pressure question. I should probably be answering in units of pressure. On the exam, it would say answer in units of atmosphere. Okay? So you say, oh, I want atmosphere. Okay? I'm going to grab this R. Okay, there's your atmosphere. That's where our pressure units are coming from. Then you say T. Of course, T has to be in Kelvin because R is in Kelvin. So I'm going to put this into Kelvin as well. And then you will correctly punch these numbers into your calculator, and you will get 1 out of 20 questions right, at least. All right. I got 6.4. Again, what really showed up on this in terms of colligative properties? Did we consider at all, did I need to know how sucrose interacts with water? No. Osmotic pressure just depends on a concentration unit. It just depends on the moles. How much stuff did I dissolve in that solution? All right, we'll swing back to kinetics. What was the average rate of appearance of NO2 from 50 to 100 seconds? Okay. Do your best to approximate here. If this were the actual exam, either those points would be labeled or would be like epically clear what concentration it is. Or it'd be in a table. Okay, so you're going to start again. I always recommend look at your axes. I'm tracking NO2 as a function of time. So I want to know these two data points, okay? Delta NO2 over delta T, okay? So I'm going to grab 100 minus 50, because we go final minus initial. I called this 0.0065 minus 0.0079. Again, that's the part where we'd be more specific for you. So that's negative 2.8 times 10 to the negative fifth molar per second. Because I called this the average rate of disappearance, that disappearance sort of takes care of the negative, okay? So again, this question might more explicitly say, hey, what's negative NO2 over delta T? Because it's standard to present all rates as positive numbers. So you might report this at the end of the day as 2.8 times 10 to the negative fifth, and call that the disappearance of NO2. All right, so we want to take that value, okay, and we want to relate it to the appearance of O2. All right, we can use that equation that I presented to you and the book uses, or you can just think about it as stoichiometry, okay? In that period of time, for every second, I lost 2.8 times 10 to the negative fifth NO2. Right? And I look up at my balanced equation. Okay? Every time I lose 2 of that, I make 1 O2. So my rate should be half. Right? The way I would write this out is to say 2.8 times 10 to the negative fifth, and that's in molarity. That's in moles of NO2 per liter over, oh, and you need seconds there too, okay? And then I'd say, here's what I'd actually do. Then I'd say, okay, well, for every 2 moles of NO2, I make 1 mole of O2. Okay, so now I'm going to cancel out moles of NO2 and be left with moles of O2. This math is the same as that equation we used from the book, but this is easier in my mind. That every time I make 2 moles, we're just using the stoichiometric coefficients, the mole ratio from our balanced equation. Every time I make 2 NO2s, I'm making 1 O2. Okay, so I should wind up with half the rate. Yes? We're in the home stretch. Just 15 minutes left. Okay? Stay with it. Okay. Real throwback question. First day, second day kind of stuff. Which one of those 2, NaCl or hexanol, will dissolve in hexanes? Which is more soluble? Let's go NaCl 1, hexanol 2. Good. NaCl, a salt, an ionic compound, will not dissolve in hexanes, a nonpolar solvent. For a salt to dissolve, for NaCl to go to Na plus Cl minus, we have to offer these ions must have strong ion solvent interactions. Okay, that's got to be ion dipole. That's really what I'm saying, right? Hexanes don't have a dipole. It's nonpolar. All those carbon-carbon, carbon-hydrogen bonds, those are nonpolar. And so it only experiences dispersion forces. It cannot, delta, in other words, what I could write about this is that delta H mix, while it's negative, is not negative enough to drive this process. Okay? Hexanol, yes, it has this alcohol, but it's got a big long tail. that's nonpolar. That will mix well with our hexane, okay? So hexanol should dissolve in hexanes. I would expect NaCl to be insoluble in hexanes. All right, let's switch it. What if I put those two in water? Which one of those two dissolves in water? Good. Salt dissolves in water for the reasons we just talked about. Because Na plus and Cl minus, when those go into solution, when that dissolves, I'm going to have a bunch of Na pluses, and water is going to orient all of the oxygens around that positive charge. All of those are partial negatives. So we get a bunch of these really relatively strong intermolecular forces, the strongest intermolecular forces. We get a bunch of them around that Na plus. Okay, so now when I think about the size of delta H mix is a big negative number, and this drives the solution process. Say that again. Why does nonpolar dissolve in nonpolar? Because entropy pushes that forward. So they interact with each other. There's like not a huge difference in their intermolecular forces, but you increase the entropy of the system. And remember, entropy was also pushing things forward because things like to be in high disorder. Okay? That was like the original premise that we say, hey, if I have two gases that are separated by a partition and I pull that partition out, the gases mix. There is something, entropy pushes mixing forward. It almost always encourages the mixing process. Okay. All right. Methanol. All right, so this is I'd read this, I say methanol has a vapor pressure of 94 torr. Ethanol has a vapor pressure of 44. I'd stop myself there and say, this is a Raoult's law question with two volatile components because I got two vapor pressures. So when I think about what's going into the vapor phase, I need to think about both of these components, both methanol and ethanol. All right? So I make a 50-50 mixture of by mole, so 0.5 mole fraction of each, and then I ask you these two questions. The moles of methanol in the gas phase is less than, more than, or equal to the moles of ethanol in the gas phase. So which one will you be answering tomorrow? I know we have done a lot today. Like, we're just building your stamina for the exam tomorrow. All right, what are you guys picking? Good. Seeing a lot of twos. I agree with the twos out there. Why? I read this and say methanol has a higher vapor pressure. It's more volatile, more likely to go into the gas phase. All right? And since there's 50-50 of it in my cup, then I just need to know, oh, which one's more volatile? That one will go more. There will be more of it up in the gas phase. Okay, so even though they're equal in the liquid phase, I would expect more methanol in my vapor phase. Okay? We can also look at this quantitatively as we do this part of it. What's the total pressure? Well, you'd remember that the total pressure is going to be equal to the pressure of methanol plus the pressure of ethanol. All right, that should make sense. Those are the two things that I have in my container. They're the things that are creating the pressure. Okay, those particles of methanol and ethanol are beating against the walls, exerting pressure. Each one of those is going to be dictated by Raoult's law. So the pressure exerted by methanol will be the mole fraction of methanol times the vapor pressure of pure methanol. And the same is true for ethanol. All right? So now I can plug numbers in and solve for the total pressure. And the math was nice in this one, right? Okay, so I wound up with 69 torr as my total pressure. And I could have split that out and said, well, 0.5 times 94, that's 47 torr. That was the contribution from methanol. All right? So the mole fraction of methanol in the gas phase would be equal to 47 divided by 69. Because remember, the pressure is proportional to the moles, and that's through the ideal gas law. So N PV equals nRT, so N equals PV over RT. This is constant. So my pressure has to be directly related to the number of moles. So methanol is exerting a larger pressure than ethanol. So it must be accounting for more of the particles in the gas phase. Okay. All right. Another day one question. Just make sure that you remember how delta H of what delta H of the solution is, okay? You don't get this equation, but it's a straightforward one. Delta H of the solution is equal to delta H of the solute plus delta H of the solvent plus delta H mix. Let's remind ourselves that these two are always positive. Those two are always endothermic because we're breaking interactions. And we're breaking IMFs. Okay? So that's my cost. How much does it cost to break up my solute and solvent? But then there's a benefit out of this, right? I get to bring the solvent and solvent together. That is exothermic. That's represented by delta H mix. This is always negative. It's always exothermic because we're making IMFs. So then the question about the whole solution process is, what is this balance between the cost and the benefit, right? Did we release more energy than we consumed? Then that would be exothermic, okay? So in this case, it's just plugging in numbers. It's 70 plus 65 plus a negative 150. That gives you a negative 15 kilojoules per mole for the overall process, which means it's exothermic, which means heat is released. So this should feel warmer, okay? When I put the solute and solvent together, I must have formed strong intermolecular forces. That lowers the potential energy of the system. Okay, so A plus is B. I feel like my mic just quit there. Okay, so that would be beforehand. When I mix them, now I have A, B, and it's lower in energy because these are stronger interactions. So that's my drop in potential energy, right? This is higher potential energy, and now we're at lower potential energy. We cannot create or destroy energy. That is the law of conservation of energy. So that difference, that is what is released as heat. And that's why it feels warm. Okay. I think we can do one more question, and for the ones we don't get to, I already have answers posted, so you can go and look when we're finished. Okay. Check out this graph. What chemical What chemical reaction best represents this graph? All right. We've got A, B, C, D. Count those as numbers. 1, 2, 3, 4. Which reaction are you picking to represent this graph? All right. Hopefully, well, I guess I didn't give you any well, no, you should, there's two that I would immediately eliminate. B is growing in. B and C both have to be products. I'm not going to pick A or D, okay? Because B is listed as a reactant, and I'm not losing it, I'm making it. Okay, and then the second part is how does the stoichiometry relate between these things? I'd say I started up here with A, and I ended there with C. So my C and A should be the same. So I want coefficients that are the same for those two. That's C. Okay? And then my question for you, we know that this depends on A, or A is our reactant. Do we know something about the order? Can I tell you that it's 0 first or second, or can I eliminate any of those? Okay? This would be a hard one to give you on the exam. Is it 0 order? No. That's the only thing I could tell you about this right off the bat, that it is not 0 order, because my rate is changing, right? If it was a straight line, it would be 0 order. But my rate is changing. That speed, that slope is changing as this progresses. So it's definitely not 0. And then you might have wanted to say, oh, it's probably second order because I have 2A. If it was an elementary reaction, then I could definitely say it was second order. But I don't know if this is a single step or multi-step. So without more information, I can't tell you if it's first or second order. Okay? And then lastly, did the pressure of this vessel, let's say that this was what I meant to say, which was pressure. All right? This was gas phase. Did it increase? That's for 1, decrease, or stay the same? What are you guys answering? Good. I'm seeing some ones. That is correct. Notice at the beginning, I started with A. At the end, I have the same amount of C, but I also have B. So I should have more particles in that vessel, which will relate to a higher pressure. All right. Office hours right after this, Evans 2004. My answer key, which is tidier than what I did today, is already posted. Good luck tomorrow.